In this clip, we will talk about basic concepts of probability theory. And we'll focus on a simple model. In this model, we will have a bag with a bunch of objects inside. And we pick one object out of the bag without even looking. And we'll try to reason about the probability of getting objects with certain property. A more axiomatic treatment of the probability theory we cover in later classes. This model is usually referred to as an Earn model. This is from in 17th century by Jacob Bernoulli, who wrote a book on probability theory. Okay, so in this model, in this first part, we're gonna look at the case where we pick an object out of the urn and of a bag once. There are some other situation where you pick one object and then you return it to the bag and then you pick it again, and then we'll cover that later on. Okay, so in this simple model, we have a bag that contains n objects. They all have identical shapes and weight, so that we are equally likely to pick any one of them. Okay, therefore, if we look at one specific object in this bag, if you pick one object from this bag at random, the probability that you're gonna pick this specific object that you have in mind is what? Oh, all right, because they are all equally likely, then the probability is 1 over the number of objects. All right, so now if you're not interested in just one particular object, but for objects with certain properties, now what would the probability of picking an object that has that certain properties is what? So because each object is equally likely to be picked, and if you have many objects with this property you are looking for, then you have higher probability, and the probability that you get that an object you pick has this property depends on the number of objects with the property, so it's exactly this. So let's look at our example. In this example, we have a bag with 7 balls, and each ball is either black or orange, and each ball has an alphabet on it. Okay, so what is the probability of picking a ball with alphabet A? All right, so we have to find where the objects are. So we have only one ball with an alphabet A, right? So therefore, the probability that we're gonna get this ball is 1 over 7. All right. Now, so what is the probability of picking a black ball? All right. So again, we have to look at this bag and find all the black balls. Okay. And there are 4 of them. Therefore, the probability of picking a black ball is 4 over 7. Easy, right? And what is the probability of picking an orange ball? Yeah, easy. Again, these are the orange ball. There are 3 of them. So you get 3 over 7. And what is the probability of picking a ball with alphabet E? Again, there are 2 balls here. So it's 2 over 7. All right. Let's talk a little bit about the vocabulary that we're gonna use later on. We're gonna refer to when we perform a random experiment, we would get an outcome. Okay, like this on the back, we pick out one ball from it, right? So it's an outcome, and sometimes this is called a sample because you pick something from something, right? But using the terms outcome is more general because later on we will talk about random experiment, and you're probably not gonna get a single sample from it. We're gonna do something more complicated. So referring to this as an outcome is more appropriate. Now, a sample space is a set of all possible outcomes. So in this case, in this our blue bag, this is the sample space. So it's a set of all objects in the bag. All right, so let's continue with another example. So what is the probability of picking a ball with alphabet E or an orange ball? All right, so you have to find all the balls with these properties, right? So it's either or, right? So it's an or. So an orange ball or a ball with alphabet E. So there are 4 of them. Okay, so the probability is 4/7. But if you look carefully at this situation, we want to find a ball with alphabet E or an orange ball. It's not that we're looking at one property alone, right? So we are looking at 2 things. One is this set is the ball with orange, and another set is this ball with the E letter, right? And now we have the vocabulary to talk about outcomes and sample space. We're gonna talk a little bit. We're gonna define another word called an event. An event is gonna be really useful when we want to talk about something complicated like this. So an event is just a subset of the sample space. Like when we talk about picking an orange ball, this is an event, right? You can see the light blue bag inside the bag. And also we usually refer to an event with some variable E here. Okay, so if we have an event E, we denote by P of E the probability that event E has occurred. So we're going to use this notation throughout the course. Okay, so you have an event. An event is just a subset of the sample space. All right. So with this vocabulary of set theory, we can do many things. Okay, so we can look at the previous situation. If we let an event A be an event that we pick a ball with alphabet E. So which one is event A? So it's this one. Okay, and an event B be an event that we pick an orange ball. So it's this one, this ball. So the probability that we pick a ball with alphabet E or an orange ball is the probability of this event. Okay, so we have an event A union B. And what is the probability of this event? It's 4/7. Okay, so let's have a quick check before we end this section. Okay, so let A be an event that we pick a black ball. Again, where is it? Black ball. Let's try to circle it. Okay. Okay. Alright, the black ball. And let B be an event that we pick about alphabet E. So it's this one. Alright. So what is A minus B? So it's this set. Okay. So only 3 balls left. So the probability of A minus B is 3/7. Let's have another quick check. Is it always true that if you have the probability of a union of 2 events equals the probability of the sum of the probability of each event? Yeah, let me give you a few seconds to think. This is not true, okay? Because from the previous example, we saw that the union of event A, this one, and this one is this is equal to 4/7. But the probability of picking an E is what, 2/7, and this one is 3/7. If you add this up, then this is not equal. So this is not always true. Okay. The question is it possible that for some pair of events, this equation is true? Like, is there any two events such that the union of the probability of the union of the event equals the sum of the probabilities of the events? So can you find some example? So I give you a few more seconds to think. All right, there are many, right? I should say the answer is yes, right? So that you can wait. But anyway, there are many. For example, if you have the set, the event A be the set of the subset of ball with black balls, okay, and event B is the event that you pick an orange ball. Okay, so the probability of the first event is 4/7. The second one is 3/7, and you sum it up is 1. And the probability that you pick any ball is 1, right? So that's one example. But you can find more, right? For example, if you have this set A or B and E, right? The event that you pick A or B, or an event that you pick E, the union of these two events satisfy this equation as well. And but an easy mistake can be people usually make this easy mistake related to a union of events. Like you have this, you know that you have a program that only crash because it has a bug or it has a network problem, and you figure out that the probability that it crashed because it has a bug is 0.15, and the probability that it crashes because it has a network problem is 0.007. And so the probability that it crashes is this. But this is not always true, because it might be the case that there's some right. So you just add this up, because this is the only way a program could crash. So you take the union, and so you have the probability of the union becoming the sum. But it might be the case that the program crashed because it has a bug, and at the same time it has a network problem. So you might not have this. So this might not be true. Okay, so it's a mistake that I made, and many people have made before. All right, so I'll stop with this question. So for this segment, we talk about various concepts, and we see that we cannot just add two probabilities, but sometimes we can do that, sometimes we cannot. So I'll let you think before you continue with another segment of this week, that under what condition that this statement is true. Okay, I'll see you next.